Let's talk about the method of sections as applied to trusses. After this lecture, you should be able to determine the force in particular truss members using the method of sections. And it's a method that is superior in many cases to the method of joints, because while you could calculate the loads or the forces in all of the members, often you don't really need to. Often you just want the force in particular members, and this method of section allows you to find those forces directly rather than having to step through the entire truss and all of the joints. Now, of course, there are example problems in the slides that I won't go through. I'd like you to open the slides, look through those problems, as well as the group solving problems, and hopefully that way you learn more on this topic. So what applications are there? Well, there are tons, because most of the time truss designs consist of quite a few number of members, and if you have to go through and solve every single joint, it's going to be quite a pain. And again, often all you really want is the force in particular members, and basically this method of sections you can think of as sort of a shortcut to get to those loads without having to calculate the load in all the members leading up from the support reactions to the members you're actually interested in. So very often trusses are made with so many members that this method saves you time when all you need is the force in particular members. So how do we do this? What is the method of sections? Well, it simply involves taking a section of the truss and analyzing it. So imagine a cut line, AA, through the truss, and you want to place that cut line, at least that imaginary cut line, so that the members that you want to know the force in are cut by that line. That's really important. Otherwise, you won't get the forces in those members. Now remember that these truss members, these are all two force members that are either in tension or compression. So when you imagine cutting them in their center or somewhere along their length, you will find the same amount of force as would be at the end of those members applied to the pins. And so taking this internal cut, we'll end up with the same results that we would have from the method of joints. So how do we do this? What are the steps for analysis? Well, the first thing to do is decide where you're going to quote-unquote cut the truss and what will consist of the free body diagram. And you really need to be careful here, because you don't always cut the truss along lines where you'll immediately get the forces in all the members that you desire. Sometimes you have to take a cut because the equations work out very well for it, work out easily. And whatever cut you take, you can't end up with more than three unknowns, because we simply won't have adequate equations. At least in 2 dimensions, we won't have any more than 3 equations to solve for the unknowns. So the maximum number of unknowns should be at most 3. Once we've decided on the cut, then it's usually beneficial to select a side of the truss, because you can select either one, you'll get the same result, but select a side of the truss where you minimize the number of terms in the resulting equations. And what that usually means is you minimize the number of reaction plus externally applied loads to the truss, and that way there's just fewer terms in your equations. It makes the analysis easier. Finally, if you need reactions, which you don't always, but if you need reactions, draw a free body diagram of the whole truss, get those, and then go back to your method of sections. Notice in this particular example, there's a left-hand side of the truss and a right-hand side. The left-hand side has an externally applied load, whereas the right-hand side requires analysis of the reactions. So it would be wise to select the left-hand portion of the truss to analyze, because you won't have to mess with any of the reactions. You won't have to actually accomplish step 3, because you don't need the reactions at D and E. You can simply use the externally applied load, the left-hand side section of the truss, and calculate all of the forces in the 3 members that have been cut. So be wise about that. Don't always go for the reactions, although I'm sort of in the habit of doing that. Sometimes you can get away without the reactions, so look for those opportunities. The final step in the analysis is to draw a free body diagram of the selected cut part, which is, of course, selected very strategically. and indicate all the unknown forces in the various cut members. Now, it's wise to always assume that each of the cut members involve tensile forces. And so you draw a force on the member away from the joint, away from the member that remains after the cut. And what you're doing is you're just assuming tensile loads in all these members. If it turns out that one of the forces you compute is negative, then that member is in compression rather than in tension. Now, again, I'm not always perfect at doing this in my examples, but it's something that's recommended. You'll notice in the example here that F sub GF has been drawn as a compressive load rather than tensile. And so if you know for sure that the load will end up being compressive, then that's probably okay. But to build good habits in your homework, you should probably just draw all of your forces as tensile forces on all the members and let the math work out whether it's actually compressive or not. Finally, once we've got it all set up, then we can apply the scalar equations of equilibrium. Now notice that there are going to be three equations. There's going to be a sum of force in x, sum of force of y, and a moment equation that will allow you to calculate all three of the unknown loads, which would be the maximum number you could accommodate. Now, there are often shortcuts for calculating things. For example, if you look at this truss and you're thinking of summing moments, if you sum moments about, let's say, point A where the 1,000 Newton load is applied, well, FGF will not appear in that moment equation because it has a zero moment arm relative to point A. But FGC and FBC will both appear in that equation, and that's going to be a little bit of a pain because FGC's moment arm is not obvious. It's not trivial to compute. However, think about it. If you sum moments about point C instead, now that may seem strange because, wait a second, I thought we cut off point C. Are we dealing with the right or the left-hand part of the truss? We're still dealing with the left-hand side of the truss where we have the externally applied load. But we can still sum moments about point C even though we've removed that portion of the truss. So if you sum moments about point C, notice that FBC and FGC pass through C, but FGF does not, and the moment arm of FGF is trivial. The moment arm of the 1,000 Newton load is also trivial, and so it'd be wise to sum moments about point C because it'll make the equation easy, and you'll end up with just one unknown in the equation, and that would allow you to calculate FGF and then sum forces in the horizontal vertical direction and calculate those. Of course, your proper solution strategy would be to sum forces in the vertical direction afterward, because then only a component of FGC would be able to resist the 1,000 Newton external load, and so you'd get FGC out of that equation directly, and then your final equation, the best method would be to sum forces in the horizontal direction. So look out for those shortcuts, look out for those opportunities to keep the equations as simple as possible, reduce your algebra effort required, and hopefully reduce mistakes that way.